Good morning, everyone. Welcome to the second day of our workshop. And today it's my pleasure to introduce Jonathan Kress, who is going to tell us about separation of variables. Please.
Thank you, Holger. And thanks to the organizers for inviting me. I think I'm here to learn some new things, and this is probably one of them, actually, because I think probably everyone assumes I know all about separation of variables because I worked a lot with Ernie Calhoun's and Willard Miller. It probably almost had the opposite effect because they knew everything already and I didn't. So I did manage to work Nijenhuis into this talk because, of course, it is connected with separation of variables. And I guess my connection with separation of variables was working with Willard Miller and Ernie Calhoun's after they had probably well, they were no longer really working on separation of variables, and they were much more interested in superintegrable systems. When I was working with them, of course, they were interested in that because of the connection with separation of variables, and special functions. They were most interested in special functions. Okay, so I guess maybe this is just three things I was looking at most when I was putting this together. Ernie Calhoun wrote a book in 1986, which was essentially sort of collected together results that he and Willard Miller had been working on in the 1980s on separation of variables. And it starts with a bit of an introduction for what was already known. And so I'll sort of, I guess, so there was already most of the machinery there from Eisenhardt and people like that. And Ernie and Willard, Calhoun and Miller, extended this to the results to n dimensions and all constant curvature spaces, and even perhaps beyond that a bit. Well, I mean they wrote down conditions that went beyond that, but didn't always look at didn't look much further than constant curvature spaces. One nice paper. Actually, Michael Krapp has written a lot of nice papers, which I usually find to be the best source of information on things that I don't understand in this area. So I put one in here. That was at the DGA conference in Prague in 2004. And it's just a sort of survey. I think it's mostly a survey of other results, although maybe some new things. And much more recently, I've been working with Konrad Scherbel and Andreas Vollmer on superintegrable systems that sort of came out of Konrad's approach to separation of variables, and that was work that he did while in Jena with Vladimir Matveyev, and so certainly that is bound to have lots of good connections. And this particular paper, he wrote several papers. This one has the most provocative title, which I thought was appropriate given Vladimir's questions about whether everything was done. But actually, his question was, are orthogonal separable coordinate systems really classified? Was actually a sort of a different question. He was, well, I guess suggesting that the classification that existed was, I guess, more of a list without really the structure on that list highlighted, and the structure being a projective variety with the action of this natural sort of symmetry group on that graph. Although I expect that Ernie Calhoun and Willard Miller might perhaps feel that they knew some of this already, but it just wasn't in their, the vocabulary is different, we'll say. Okay. So where did this story start? Well, actually, I probably don't really know, but certainly the idea separation of variables is probably most simply, well, starts with the geodesics on a Riemannian manifold with a metric G, and the geodesics are the flows of the Hamiltonian vector field, or given the flows of this Hamiltonian function on the cotangent bundle, and a classical sort of method for solving the for these is to introduce a new function on M of the position coordinates. So the P's are the momenta coordinates on the fibers of the cotangent bundle, and the X's are the coordinates on the base manifold. And so the, I guess, classical method for solving for the flows is to introduce a new function W, and the momenta are given by, I guess, the gradient of W. And perhaps this can be solved with, well, with a bit of good luck, if the solution has this nice form, the sum of n functions, each depending on just one variable. So this is an n-dimensional formula. And if that's possible, we say the Hamilton-Jacobi equation is separable, and the xi are separable coordinates for this equation or this metric or something. So usually the sort of terminology is, people say the metric is separable, the coordinates are separable, whatever, but something separable here, and it's the Hamilton-Jacobi equation. Okay, so when the metric in these coordinates is diagonal, then we say it's orthogonal coordinates.
Sorry, I don't understand. What's the relation of S?
Oh, sorry, it's a typo. That's the relation. I started out with S's everywhere, and then on the next slide I started using S's for something else. I thought I'd better go back and change it later, but I forgot to change that S. Sorry, yes.
So it should be W?
That S should be a W. Yes. All right, thank you. Okay, so when the metric is diagonal in these coordinates, we say the coordinates are, well, the separation is orthogonal, zero orthogonal coordinates.
But S also depends on P's.
No, the P's are like dn or ds, dw. There's no S.
Yeah.
dw by the x1 is p1.
Well, that's the definition.
Yeah, that's it. Well, yeah, part of the ansatz, I guess. Yeah, I mean, it's right. Yes, the pi is the partial derivative of w with respect to xi. So why you can do this is a whole other theory. But, I mean, it's, okay, I guess it's Jacobi's method for solving Hamilton's equations. Make this postulate. Okay, so Stackel in 1891, and you can find this paper. It's not too hard. Gave some necessary and sufficient conditions for the Hamilton-Jacobi equation to be separable, I guess. It's a complete integral, depending on the via separation of variables. So here, I've probably written this wrong around. Actually, I think I took this from. I took this directly from Ernie Callan's book. So here is the Hamilton-Jacobi equation, and now we've got a V. You can ignore that. V was 0 in the previous slide. You can just put in a V if you want a potential. So this is just the same. So here we've got a diagonal metric where the diagonal components are just these 1 over hi squared. So it's the same equation as before, Stackel said it admits a complete integral. You can solve it if there exists some matrices in the right form, and this was called a Stackel matrix. And essentially, these hi that are given here have to be some components from that matrix divided by the determinant. And this S, so the matrix is S. SI1 is the one I cofactor. Maybe it's I1. Maybe I got that wrong. It's a cofactor, and they all have the one in it. So it's one column, I think, is going to be the one row. So the this is a cofactor of S, and the components. This is this indices down. These are the entries in the matrix S. Depend only on a single variable. So the ith row depends only on the ith coordinate. Okay, it's just a very special and sort of restrictive sort of form. And so he says, you know, here is the complete solution, but he sort of left to find what are the possible things these could be. So he also gave, so actually you see, yeah, this S, these HIs will have a, well, they depend on this cofactor, matrix of cofactors with a 1 here every time. Of course, there's 2, 3, 4 up to n as well. And they essentially give you additional quadratic integrals of the motion. So so there's this H is a sort of distinguished one from this Stackel matrix with a 1 here, and the other ones turn out to give you other quadratic integrals, and they all Poisson commute. So that's sort of essentially everything you need for an integrable Hamiltonian system. Okay, so so that's sort of, I guess, the main.
Very easy now to make integral systems, right? You just write down a matrix.
Yeah.
Property. And then
Yes.
compute its inverse on the cofactor.
And there you have it. Yeah.
You have a separable.
Yes. Yes. I guess the question what people wanted to ask was, when do you get ones on, you know, Euclidean space or something that you wanted to get?
So W must be of the form which you showed in the previous slide, right? W x1 plus W2 x.
Yes, that's right. Oh, so that then, yes, that's right. Yes. Should I have a? Well, I guess that's right. So I mean, you could put a WI because these W's. Well, if these conditions hold, then you can separate it, and it's just a redirect. I think I meant to cut this slide out, but anyway, it's in here because it was the next chronological thing. Levi-Schreiber gave some conditions for the metric to be separable in orthogonal coordinates at this time. Well, you can Ernie's book and other places, it's the original paper, tells you how where this comes from. But it wasn't very useful, I guess, because well, not directly, because essentially it's if you have a set of orthogonal coordinates in which separation occurs, you can plug that into this equation and verify that they are separable coordinates. But if somebody said to you, here's an equation, solve it, that would be hard. Right, so wasn't, I guess people didn't find this very useful for actually finding separable coordinate systems. If you had one, you could check that this condition was satisfied. Robertson looked at separation of variables for the Helmholtz equation, and of course the Helmholtz equation uses the Laplacian for the metric. So this is in some sense, these natural second order differential operator on a Riemannian manifold, and this equation obviously it's well known. And the separation of variables, you can show that if you have separation of variables for the Hamilton-Jacobi equation, or orthogonal separation of variables for the Hamilton-Jacobi equation. Then you also do for the Helmholtz equation. So the separation for the Hamilton-Jacobi equation is additive, and for the Helmholtz equation, it's multiplicative. So you have a form like this with some sort of not constant, but fixed factor out the front, perhaps. So it's not it's not necessarily completely a product of functions of one variable, but it's up to some overall factor. But it's not quite a one-to-one correspondence. You also need to have an additional condition, and Robertson gave a condition for that. So he was studying this separability of this equation like this, and his additional condition, I don't know, it just well, I haven't written it down here because Eisenhardt reformulated it into something much nicer, which was just the requirement that the Ricci tensor is diagonal in the coordinates. So if you look at Robertson's condition, it just says you have to have some derivatives equal to some arbitrary function in this form. Good luck. And then Eisenhardt said, actually, this has got a nice geometrical meaning. In that same paper, he also reformulated Stackel's theorem, I guess, in a more geometrical way as well. Because Stackel's theorem, yes. Yes.
So this is if and only if.
Yeah, yes, it is. I think it's if and only if, yes. Okay, so Eisenhardt, as I said, he in his paper in 1934, he looked again at Stackel's work, and I mean, it's clear he's working on it. It's not like he's doing something separately and came to a similar conclusion. He's referring to Stackel's work, and I guess it's starting to move towards the sort of more modern approach because, well, he's still talking about quadratic integrals, but he formulates the conditions that you need for the Stackel system as the Poisson commuting of some quadratic integrals, and so these quadratic integrals are the functions of momenta and position, quadratic in the momenta, and they have to Poisson commute. So his theorem, which parallels Stackel's theorem, says you need n independent quadratic Poisson commuting integrals, and those integrals quadratics. I mean, they have there's a quadratic form associated with which can be considered as an endomorphism on vectors or covectors, and that endomorphism had to have n simple roots, or n simple eigenvalues, and a common eigenbasis for all of the n independent quadratic forms.
Are they in case?
Oh. Shh. Yeah. Okay. So given the involutive family, separability then becomes an algebraic condition on those on the sort of quadratic forms. Okay, so and in that paper, Eisenhardt also classified all the separable coordinates on. Well, he did it more concretely on E3, Euclidean space, and he comes up with coordinate systems which have coordinate planes that are confocal quadrics, what you expect. And on S3 on the sphere, he doesn't sort of write them down explicitly, but he sort of gives a parameterization for the quadratic forms, but doesn't sort of explicitly write out the coordinate systems. Okay, so then in the 80s, Cowlins and Miller, I guess, continued this work. They had a number. There's a sequence of papers. If you look on Miller's website, it's easy to find because they're all joint, well, almost all joint papers, and they've got a different paper for separation of variables of the Laplace equation, on the hyperbolide, and the Helmholtz equation on this other surface and things like that. So there's a whole sequence of papers, but there's also ones which are about more general conditions on just a Riemannian manifold. Not that they could classify them, but they have written down the conditions, and they're essentially the same as Eisenhardt's conditions, except they refer to, instead of the quadratic forms, they start talking about Killing tensors, because the quadratic form, well, the components of the quadratic form give a Killing tensor on the manifold. And they, Ernie Cowlins has got a book where he then goes sort of collects some of these results, and it gives a complete list of the separable coordinates on n-dimensional Euclidean space and the sphere. I can't remember the hyperboloids in the book, but so essentially it gives a sort of constructive approach to how you can generate, well, all of the possible coordinate systems in a particular dimension point, and you have a sort of a tree where you're making decisions as you go down about whether you're going to attach a sort of spherical coordinate system here or a parabolic one here as you sort of branch. Like you take it, start with 2 dimensions, and then you say, well, one of those variables, I'm going to split it into 2 variables, and they're going to attach an angular coordinate here, or I'm going to make a parabolic coordinate sort of in this block, and so on. So they have they sort of classify them all, and it certainly is claimed that that it's if and only if they have everything, and I think I believe that's true. I mean, the way that Ernie Cowlins was working on this, I think, was that coordinate systems are, of course, if you rotate your universe, then you'll have a new coordinate system which is just related by rotation. So they were classifying coordinate systems that were equivalent up to the sort of natural isometry group on the Euclidean plane, Euclidean space, Euclidean group, and on the sphere, the rotations. And they also did conformal ones for the last equation. So they classify coordinate systems up to equivalence by the isometries. And I think what Ernie was doing was looking for a sort of a normal form for your Killing tensors, well, you could say let's assume there's one of a particular type. What do you get? If you add another one, add several more, can you rotate it to kill them off? And just sort of come up with normal forms for the possible spaces of n commuting Killing tensors. This is what I imagine he was doing, given what he was suggesting I do when I was looking at superintegrable systems. But there isn't really. I don't see that in his book. I mean, he goes through a sort of case by case analysis where you say, now there's these possible cases. So someone could dispute that maybe there might be more. There's something I don't know. Okay, so this is a sort of typical looking metric. Oh, I should have a, sorry. This is just the components. Oh yes, this is the components. Yes, GII. So this diagonal, because it's orthogonal coordinates, and the diagonal components are just given by things like this. So I guess these xi and x, the x's are, I guess, just the usual places on the n sphere. So these are yeah, I think these are coordinates on the sort of ambient space. So this would be subject to the sum of the squares is equal to 1 or something like that. Yeah, that's one more E. Yes. Yeah. Okay. So yeah, that's an important point here. There's one more E. There's n plus 1 E's and n X's here. And so I mean, this is just a product of different factors with different distinct E's, and have to do with the focus, the structure of the ellipses. And and the product on the top here of just differences of the coordinates. You can just make everything complex and write down something complex as well, but then and you can then sort of take the real sort of sections from that to get hyperboloid and the sphere and various things in the Minkowski space and things like that. Okay, so the coordinates themselves on the sphere, these S's here are different. No, these S's here are actually in an ambient space because there's n plus 1 of them. And if you sum up these sums of these squares of the S's, you should get 1. You can try it now. I'll give you a moment. Yeah, so this is like a coordinate transformation that lets you go from a sort of ambient Euclidean space to some to the coordinates x, the x's on which are coordinates on the sphere. One thing to note here is that, of course, you can't have E1 and EI and EJ equal because, well, we don't want that. Oops. Giving it away. You don't want EI and EJ equal. This is like the sort of most generic set of coordinates. Actually, if you, as you sort of allow E1 and E2 to go closer and closer and closer together, you'll get certain well, you can sort of animate this if you want and see how the surfaces compact up and jump to a new regime, which is a different set of sort of degenerate elliptic coordinates. So there's a whole, this isn't the only one, there's a whole lot of other ones. And then there's sort of a hierarchy from the most generic one like this. If you let two roots coalesce, then you get a different coordinate system, and another 2 roots coalesce, or and so on, and you get this sort of distinct structure of these elliptic coordinate systems. And so this is another way to generate them all, apart from, although that, yeah, they were worked out from the ground up. Look at all the possible cases, but then you can see how they're connected by these degenerations. Okay, so another perhaps different approach to separation of variables comes from Benenti. And obviously it's obviously connected, but so Benenti, I guess, I mean, he did have the Poisson commuting integrals in there, but where did they come from? The sort of the controlling factor was, well, the starting point was a single tensor. So in Eisenhardt and Stackel, I think that there were these n commuting tensors, which are sort of like in there from the start. With Benenti, he has a single tensor, and from that you can construct the n commuting integrals. This the Benenti tensor, I think he did not call it a Benenti tensor. He called it an L tensor after Levi-Civita, I think. But since then, later, other people have called it a Benenti tensor. Satisfies an equation which looks remarkably like the Killing equation, or similar. Actually, it looks like the conformal Killing equation, except there's no symmetrization. So it's often called a special conformal Killing tensor. So this, if you just say that the covariant derivative of a valence 2 tensor is just whatever you need it to be. This is a symmetric tensor, symmetric in I and J, so you've got to have these 2 terms. But that's all. It's just going to be some covector tensor with a metric, and then symmetrized. That's all that's there. This condition here that alpha is the sort of divergence, I guess, of the derivative of the trace, gradient of the trace of J is a consequence of this equation. It's not an extra condition. You just contract on that and you get that. So this equation, the special conformal Killing tensor equation. So I think yes, as a result, this says a valence to conformal Killing tensor. Okay, so this is a conformal. Who knows what a conformal Killing tensor is? Hands up. Conformal Killing tensor is if you were to symmetrize this equation. Yeah. If you have a valence to conformal Killing tensor with pointwise symbol eigenvalues whose Nijenhuis torsion, this is a word I've read before, vanishes, it is a Benenti tensor. Okay. Now, what was the significance of the Benenti tensor? Well, why did Benenti like it? I guess here it's you've got both indices down, but of course we've got the metric, so you can raise it to a 1-1 tensor, and then it can be an endomorphism on vector fields, and so you can think of it just as a linear map. That linear map has a sort of cofactor. This is just linear algebra. There's the cofactor matrix, if you like. That turns out to be, well, up to some. I don't know. It turns out to be a Killing tensor. Okay, there's various different words that all sound the same here. Special conformal Killing tensor, conformal Killing tensor, and Killing tensor. They're all closely related. So not all conformal Killing tensors are Benenti tensors or special conformal Killing tensors. They're special ones. If you have a Benenti tensor, you can actually construct a Killing tensor, which a Killing tensor equation is just, oh no, it's not that. It's the symmetrized covariant derivative is 0. We should have put that up. Okay, so from the Benenti tensor, you can generate a Killing tensor, but wait, there's more. If you have a Benenti tensor, then I think we've seen this in the lectures, or at least something like this. Then you can adjust it by any scale, any constant multiple of the identity, and you still get a Benenti tensor. Okay, the conditions. It's certainly true that the metric here is a trivial solution to this, and so you can add multiples of that trivial solution, and you still have this condition, and the other conditions will still hold too. If you have so this J, I'm pointing at the board. I don't know. I assume no one's watching online. Why would they be? Yeah, I completely forgot. Sorry. So this Benenti tensor with the parameter lambda in it has a cofactor matrix, and that is actually polynomial in lambda. And each of the sort of coefficients in that polynomial must also be a Killing tensor. I mean, the equation you get here will just split up into the powers of lambda, and you can read off the coefficients. So each of those coefficients in the cofactor is also a Killing tensor, and those Killing tensors are Eisenhardt's Killing tensors. So that's how you recover the n commuting integrals from. Well, I haven't checked that they're commuting, but that's where they come from. These have also been called cofactor systems, probably for that reason. There's a Lundmark wrote some papers, and he always talks about cofactor systems. Yes.
Is this essentially a definition of a Benenti tensor, like this is equivalence, fails to form a tensor pointwise?
No, that's a result. So the Benenti tensor,
There are more Benenti tensors out there that
possibly.
aren't this scale.
It could be, yeah. This result is not saying that it's all. I'm saying if you have a valence to conformal filling tensor, yeah, then you get a Benenti tensor.
Yeah, thank you.
Okay, so yes.
So that condition is not equivalent to the diagonal torsion dimension. Or is it? I mean, for the APC.
Yeah, so I think this here is a very special condition, and it's Nijenhuis torsion automatically vanishes. I think so, but maybe this is something that should be checked. And I'm sure there's members of the audience who already know the answer. Yeah. I think yes, there's certainly an important result there, which is one way or the other. Yeah. Okay, so yeah. Okay. So now for something completely different. So this is, I guess, this is where the connection with Nijenhuis geometry comes from, or is. I mean, it is there. I mean, obviously it's there. The word's there. And this is all about whether or not the well, the integrability of the endomorphism. So another approach to separable coordinate systems was sort of I guess I already mentioned this. So much more recently, Konrad Scherbel, who was in Jena working with Vladimir at the time, was looking at separable coordinate systems from perhaps a different point of view. So at the time when Eisenhardt did his work, this was before the paper, results from Nijenhuis about of which we are considering, and I don't think Ernie Kalnins and Willard Miller knew about any of that. So their results were independent of this. But you can reformulate the condition that you want to have. You want your filling tensors to I guess produce integrable submanifolds, and which become the coordinate surfaces by in terms of some equations on the Nijenhuis torsion of the filling tensor. And I have to say, you can see this is a screenshot from Konrad's paper, and so I don't claim to be an expert on this, but so these integrability conditions are just algebraic in K and the derivatives of K. Right. So this gives us sort of another way to actually approach this problem. These are just polynomial equations in K and its derivatives. If you're interested in constant curvature spaces, flat space, the sphere, etc., all of the killing tensors are known. It's a vector space, and it's well known what they are, and they're quite easy to write down in lots of different coordinate systems you might come up with. You just look in the book and you've got the list of killing tensors, and they're not very hard to write down. So if you want to satisfy those equations, and I believe actually that this is actually a consequence of the first two, but I think that's something like that. So actually, it's even easier than it seems. If you want to look at this problem in a constant curvature space, you just write down, you say that you're looking for killing tensors which are going to satisfy these conditions. You can write down a linear combination of them. plug it in, you just get algebraic equations on the components. Okay, now obviously you'll get a million of them if you do it the wrong way. But if you're a bit approach it in a more systematic way, it's more tractable. And of course, one important point here is that whatever you get must be invariant under the symmetry group, the isometries. So these equations kind of sort of break down into irreducible pieces, which carry representations of the isometry group. So okay, so Conrad was interested in reformulating it like this, and he parameterized the Killing tensors just by some algebraic sort of objects with certain symmetries. I guess there's a well-known parameterization of Killing tensors in terms of there's well-known parameterization of Killing tensors on the sphere in terms of Killing tensors on the sort of higher dimensional space, and this is there's a whole industry in that. Anyway, the result of his work was that that actually you do get a nice and well-known algebraic variety that classifies the separable coordinate systems. I've got no idea what this variety is other than what's written there. And Conrad said he didn't either when he did it. He just happened to be talking to someone at a conference who said, "Oh yeah, that's this thing. We know all about that." And so, sort of interesting connection made with some other field. The separable coordinate systems themselves are then parameterized by, it's an algebraic variety, and you've got you can sort of break it down into pieces which are called Stashev polytopes or associahedra or something, which you have to read his papers to find out about. But anyway, there's a nice structure sort of which is seen in the coordinate systems the way Ernie Cowlands was building them up in this sort of tree diagram, putting blocks on here and here. There's a nice structure to that which is seen in other places. Okay, I was going to talk about superintegrable systems, but I only have one slide, and here it is. So each of the Jacobi elliptic coordinate systems on the sphere and flat space gives rise to a superintegrable system. Now, this actually I think is quite interesting and maybe surprising, or maybe not. Probably not surprising after you studied it for a long time. But if you pick a particular of these Jacobi elliptic coordinate systems, somehow there is in those systems there's some parameters E. So it's actually a whole family of coordinate systems. You vary these E's and you get slightly different ones. I mean, you're moving the ellipses in and out, the foci in and out, whatever. So you've got a whole family of elliptic coordinate systems of a particular type. This Hamilton, or the system here, separates in the sort of most generic elliptic coordinate system for any values of those parameters E. So you've got this parameterized family of sort of quadratic integrals that separate this system, and that then in some way leads to the generation of extra additional quadratic constants. Okay. I think because of this fact that you've actually got a whole lot of different coordinate systems. I don't really understand. This is sort of more of an observation than a theory, than a sort of theorem, I should say. But I think it's sort of interesting that each of these coordinate systems where you've got these parameters in generates a superintegral system, and you get more integrals of the motion than you sort of bargained for as a result. I think I might just maybe I'll just say one last thing. Conrad's approach to treating the separable systems as an algebraic variety is now sort of a little another project, not a little project, a big project with him, myself, and Andreas Vollmer, to do something similar for the superintegrable systems. And there are some papers on the archive where we've made this. Well, I'd say Conrad and Andreas have made a lot of progress, and I've been along for the ride, which is, but there's certainly going to be more coming. Okay, I think I'll stop there.
Yes, thank you very much. And thank you for depreciating your own new work, which you only presented in a single slide, but there will be a chance to talk more about that later. Certainly I'm interested. But anyways, so are there any questions?
I have a question. I think partly, so if I understand correctly, separation, maybe going back to my undergraduate years, separation of variables is when the solution of the system can be written in separation of variables. But
Yes.
now, I wasn't quite clear if there's also such a thing as separation of variables where the integrals are sort of either the sum or the product of functions of one variable.
Well, I think that just naturally goes together. Although maybe it's not always as simple as a sum. Might be depending on, well, it is a bit like that, yes. So the integrals do have this sort of similar sort of structure as well.
But let's say if you have integrals that have that structure, then we also always have a solution.
I think so, yes. I mean, I don't know what the result will be, but there's certainly there's a lot of results about partial separation. I mean, for instance, if, you can split the systems up into two groups of variables, and maybe and you can essentially, a lot of these sort of constructions are really like constructing a warped product on a manifold, where you've got some base manifold and you just take a product with another one with a factor in front, and sort of building it up in blocks. So there's a lot of sort of this sort of block structure in there. And this separation of variables is all about just separating into single variables, but you can, but there are notions of partial separation as well, and then the integrals will exhibit that sort of block structure as well.
So if you close or determine, so if you extend it, get all the coach and everything, and there are no bridge spaces we want to get them.
I don't think there's any classification of them. There's certainly the constant curvature spaces do, and they're essentially a particular special type of conformal killing tensor. So you've got to have a conformal killing tensor to start with, and then it could be one of these special ones. I'm sure that people have looked at which spaces might have. I don't know if there's any. I don't know about results.
Can I ask a question, Jonathan?
Sure.
So it's about the Deline Mumford Knudsen variety that you were talking about just earlier. Maybe if you could just scroll back there. And my apologies, it could be that you actually answered the question earlier. My computer crashed several times during a talk, so I missed lots of bits in the middle. So is this basically a spectral curve construction, and is the fact that it's separable?
So it does. Yeah, I really know nothing about this. I've just read, Conrad's paper and trying to remember what it is, and it's something like the it's to do with a curve of a certain degree. It's with a certain number of marked points. It has some description like that. Yes.
And is it similar to? I mean, with a lot of integrable systems can be described by some curve with a certain number of marked points via like a spectral curve kind of correspondence. Do you know whether that's the kind of thing that's going on here, or is it a different way of getting hold of this data?
I can
Not sure.
definitively answer that. I don't know.
Okay. Alright.
Yeah, but I mean, it's an interesting question. Yeah.
I don't know. I don't know much more.
Yeah.
But I think some of these are in some sense unrelated, right? This is a structure that is appears in the space when you try to classify all these systems. But what you are after is somehow, say, a particular system, and that has the spectral curve, etc.
Yeah.
This is somehow
Right, this is- yeah, that's
classifying
right,
the
yeah.
space of all systems that
Yeah. Okay.
separate in this way.
Yep.
I think
Okay.
why it is there is a kind of mystery.
Yeah.
It's an observation, but
All right. Cool. Thanks.
maybe I can ask another question. So about your superintegral system in the end, these alphas are now functions of the e's, or
The alphas.
so yeah, the
Yes.
coefficients in
Here.
Yeah.
No, they're just they're just constants. I mean, there's the parameters that they will appear in the integrals of motion,
Mhm.
but they're independent of the e's.
This system separates in a particular elliptic coordinate system, is that right?
Well, it separates in the elliptic coordinate system with the generic one where you can specify what the e's are and you can change those values and it still separates.
Oh, so you can change the e's and it always separates.
Yes.
No matter what.
Yeah.
But you have to keep them distinct as well.
Yes, that's right. Yeah.
And is that, I don't know, a characterization almost? Because usually you would think.
Well, I think that does characterize this particular
Yeah,
system. Yeah.
yeah.
I mean, this is the only system with that property for that particular for the generic coordinates.
Because in general, you think that the system separates. It doesn't mean that you can change the e's, right?
No,
Without changing the
that's right.
system, right? It's very special.
Yeah. So yeah, that's right. These are special.
Yeah, they are. All right. Thank you very much again.